Okay, so in the lab that we just completed, we looked at rolling different objects down a ramp and measuring how long they took to get to the bottom from rest. In the original demonstration, I took a wooden disc and a brass ring and I allowed them to roll down the hill, and we saw that the wooden disc rolled down faster than the brass ring. And most students thought that the two objects were going to make it at the same time. So the prediction for most students was that they would land at the same time at the bottom. And I would think that for most students, the reason for that is they think back to what they know about energy, and they say, well, at the top, the object has all potential energy, and all of that energy turns into kinetic energy. So we say, oh, mgh equals 1/2 mv squared. And if we solve that for v, we get this. So it should only depend on the height at the top. And since they started from the same height, they should have the same speed at the bottom. But our results didn't match that at all. That's not what happened. So I want to talk about how come that doesn't happen and what's really going on here. So I want you to think about, suppose we had a rigid object like a disk. So let's imagine that this is a solid disk. And it has a total mass of m. Now, let's consider one particle on this disk that makes up part of its mass. That little piece, that little particle, has a mass of little m. And let's say that it's, this wheel is, or this rigid object, this disk, is rotating around like this. So at any given time, this particle, little m, might be moving in this direction with some speed v. So let's talk about the kinetic energy of that single particle. Kinetic energy, as we know, is 1/2 mv squared. But it's not really convenient to think of it that way when it's moving in a circular path. Like at this instant, it's moving, in the upwards direction in my picture. Later on, the direction will obviously change. Let's think about if this were the center of the disk. The distance from here to where that particle is r. What we know about a rigid object is that every point on that rigid object is rotating at the same angular velocity. Even though points farther away might be moving faster in a linear fashion, from an angular perspective, all the points are moving with the same angular velocity, omega. So if we think about it in that context, we could say that the kinetic energy is 1/2 m times, instead of calling it v, if you remember the relationship between v and omega is that r times omega is equal to v. So we could say 1/2 m r squared omega squared, like this. So that's for any one given particle. We take its little mass and we multiply by how far it is away from the axis and times this quantity omega squared. So if we wanted to know the total kinetic energy for the entire thing, we would have to add up every single particle's kinetic energy. So we would have to add up 1/2 m for every little particle, how far away it is for every single particle, and multiply by omega squared. But think about the fact that the omega doesn't change. Every single particle has the same omega. And obviously, the half isn't changing either. So we pull those out and get this, and add up the m r squared for every single particle that makes up this object. So to add them all up, if we're going to count them, we could put an index on here like I. And we could say I equals 1 to n, however many particles that make up that object. So in physics, we have a term for this quantity right here. This is called rotational inertia, or moment of inertia. And what it is it's a quantity that describes how difficult it is to change the angular velocity of an object. We're going to talk about its relationship to angular acceleration later on, but that's basically what it does. So if we do that, the symbol for rotational inertia is capital I. So what we can do is rewrite the total kinetic energy for this rotating object like this. I times omega squared. So what we're going to learn is that I depends on a bunch of factors. First is the choice of axis. Where is the object rotating around? That makes a difference. So if we think about, is it rotating on an axis in the middle? Is it rotating on an axis at the end, etc.? Like if you pick up a book and hold it in the middle and shake it back and forth, it's easier to rotate than if you hold it at one end. So the choice of the axis makes a difference. Another huge factor is the mass distribution. What we want to see, and if you think back to the lab, is that when mass is concentrated close to the axis of rotation, that's going to give the object less inertia than if the mass is concentrated far from the axis of rotation. And we'll see lots of examples of this, but the ice skaters, figure skaters, are the best example that you see a lot, where ice skaters will start spinning with their arms out, and they'll spin at one rate, and then when they pull their arms in, they start spinning a lot faster. And part of the reason for that, not the only reason, but part of the reason, is because they are changing their moment of inertia. They're making their inertia less by pulling their arms and making it easier for them to rotate. The total mass definitely makes a difference. The more mass you have, the harder it's going to be to rotate. More mass has more inertia. And how far that mass is from the axis. So that kind of gets back into the mass distribution. Okay. So if we go back to our lab, the objects that we tested weren't just spinning. They were spinning and translating. They were moving their center of mass at the same time. If we think about it, they're both moving linearly and rotating at the same time. So when we go back to our statement about energy that we started at the top there, we realize that that's not quite right. The way we want to think about it is more like this. We want to say that the potential energy at the beginning is equal to kinetic energy needed to translate plus kinetic energy needed to rotate, both of them together. And we can substitute this. We could say mgh for the kinetic energy, potential energy, equals the 1/2 mv squared, which we're used to for translational kinetic energy, plus this new term, 1/2 I omega squared, which is the rotational part. And when you look at this, I'm not going to get into all the details in this lesson, but if you look at it, if we were to solve this expression for V, we would note that the answer for V is going to depend on what the value of I is. And when I changes, that's going to change the velocity the object has at the bottom. So depending on these factors that we talked about here, they're going to affect how the object rotates. And we'll talk about exactly how that works out, like I said, in a later video. But you can see that they're not all going to have the same speed. It's going to depend on these factors, which are going to impact the moment of inertia. And that's going to make more of the energy translational or rotational. And not all translation, and that's what affects how fast they roll down to the bottom.